Hello, class. We're about to start section 2-1, Avoiding Empty Pockets. Our learning objectives is to distinguish between simple interest and compound interest, to distinguish between linear and exponential growth, to interpret exponents as repeated multiplication, and to simplify numeric expressions involving exponents and order of operations. Okay, now we have a quote here by Einstein. It says the most powerful force in the universe is compound interest. Albert Einstein. Einstein was a smart guy who knew a little something about powerful forces. So that quote is a bit of an eye opener. In this lesson, we'll study interest, a subject that everyone in our society needs to know something about, unless they want to end up like our friend to the right. If you have a trust fund that would afford you the opportunity to pay cash for a home, a car, a yacht, good for you. Feel free to send us a generous donation, care of the publisher. If not, you'll need to borrow money many times during your lifetime, and the amount of interest you pay will be an important part of budgeting your money. Then there is saving money, another important part of a financial plan. Putting money in your sock drawer is not a sound investment strategy. You'll want to invest in a variety of accounts that will add interest and grow your money. In either case, understanding the power of compound interest will set you on a path to financial success. Okay, we go down here to problem number 1. It says discuss any experiences you've had with some of these important financial situations, being responsible for a credit card or checking account, borrowing money to buy a car or home, starting a savings or retirement account, or others. Okay, basically, if you bought a car, a house, or anything that required you to pay interest payments, that is your experience. If you have a savings account or checking account, that is also another experience for you. Okay, number 2. Each of the situations listed in question 1 is distinct, but all have some common traits. List any you can think of. I could tell you this one common trait if you borrow money is that they all have it where you pay interest. That is a big common trait of them. Okay, now at the bottom here it says interest is a fee paid for the use of someone else's money. If you borrow money to buy a car, you pay the lending institution for using their money at the time of purchase. If you put money into a savings account, the bank pays you for having access to your money, which they in turn can use to lend to other people. Simple interest is calculated as a percentage of the original amount of money. For example, if you deposit $100 in an account that pays 4% interest per year, at the end of 1 year, you will have 4% of $100 extra in the account. Since 4% of $100 is 0.04 times 100, it equals $4. You will have earned $4 in simple interest, and the account would now be worth $104. In the second year, you'd earn another $4 in simple interest, making the account worth $108. Now we go to the next page. It says compound interest, on the other hand, the force that Einstein was so enamored with is interest that is paid not just on the original amount deposited, but on interest previously earned as well. To help you to understand the difference between simple and compound interest, let's look at two different accounts. Okay, now we look here at account 1. Account 1, you deposit $1,000 into an account that pays 5% simple interest on that thousand each year. Account 2, you deposit $1,000 into an account that pays 5% of the account balance at the beginning of the current year and interest each year. Okay, now it says answer the following questions about account 1. Getting an answer is nice, but make sure that you think carefully about how the amount is growing and look for the pattern. Okay, so the first thing here is that we could go right here to Desmos and it says you deposit $1,000 and you get 5% on that $1,000, which is $50. So for the first year, we will have $50. Now remember, when you do interest, when you do simple interest, it's the same amount of interest each year. So it'll be $50 for the second year, $50 for the third year. So you would just keep getting $50. Now, we want to know how much is left, how much will be in the account at the end of the first year. So remember, you had that 1,000 and you would add the $50 to it. So you have $1,050. The second year, you would add another $50 to it. So you have $1,100. And the third year, you would add another $50 to it, and you have $1,150. Okay, now we'll go here to problem number 4. It says repeat question 3 for account 2. Now, if we look at account 2, the first year is still going to be $50. And then our first year, we will have $1,050 in our account. Now, this is important because remember, the following year's interest is based on the previous year's total account balance. So we will have to take this value here and take 1,050 and multiply by the 5%, which will give us $52.50. Now we will have to take this 1,050 and add the $52.50. So that will give us $1,102.50. So now we would take that amount and still multiply it by the 5%. So it'd be $1,102.50. And that would give us $55.13 in interest. And the reason why we add 13 cents is because with our money system, we only go 2 places behind the decimal. So now we would add this here, and that would give us $1,157.63. So now it says here, computing simple and compound interest. To find the simple interest on the amount of money, you multiply the original amount by the interest rate, written as a decimal, and the amount of time. The units for the time, often years, should match the units of interest rate, often percent per year. To find the compound interest on an amount of money, first calculate the simple interest for the first year and add it to the original amount to get the new balance after 1 year. For subsequent years, compute the interest as a percentage of the new balance rather than the original amount. Now, we're going to go over some problems that will illustrate this. Okay, so now we go to number 5. Number 5 says fill in the next table by finding the amount in the account at the end of each number of years. You've already found 4 of the amounts in the table, hopefully. Okay, so we have account 1 is a simple interest. It's 1,000, 1,050. Now remember, it just keeps going up by $50. So it's $1,100. It'll be $1,150. Be $1,200, and then it'll be $1,250. Okay, now we go over here to account 2. Now, from our previous page, we found out after 2 years we will have $1,102.50. And then our third year we have $1,157.63. Now we want to find our 4th and 5th year. So this is how we could do it. Remember, we have to take the ending balance, which is $1,157.63, and we'll multiply it by the 5%. So they gave us $57.88 in interest. So we'll take the $1,157.63 and we will add the $57.88 to it. So we will get $1,215.51. Now we have to take this amount, $1,215.51 times the 5%. So that'll be $60.78. So we'll take the $1,215.51 and then add the $60.78 to it. So we will have $1,276.29. Okay, now for number 6, it says suppose you wanted to find the value of each account after 20 years. Why would that be a much harder calculation for account 2 than account 1? Okay, now account 1 increases by $50 a year. So we could multiply $50 times 20 years. Okay, that's why that is easier. Just take the $50 times 20 years, and then we would see, how much how much interest we would have made. Okay, now, and then add that to the original $1,000. But here, with account 2, the interest is based on the previous year's balance. So we cannot multiply 20 to a specific amount. Because we know the interest is always changing. All right, now, to really understand the difference between the ways these two accounts grow, it's helpful to write and simplify some calculations in a particular way. Okay, now we're going to go over to page 128, problem number 7. It says, why does the value of the compound interest account grow faster? Okay. With compound interest, every year you are getting a percentage of the newly added interest to the original amount. So, like we did before, if you made $50 in 1 year and you had $1,000, which what you started with, you have $1,050 now that you would calculate interest on instead of the $1,000. So that's why it makes it a little bit more difficult. And also why it grows faster, because you're getting interest on top of your interest. Okay, now for number 8, it says here in the directions, Now let's summarize what we've learned about the growth of these two accounts. For questions 8 and 9, fill in the blank. Account 1 is growing by exactly $50 each year. So the amount after any number of years looks like $1,000 plus $50 times the number of years past. Account 2 has its value multiplied by 1.05 every year. So the amount after any number of years looks like 1,000 times 1.05 times 1.05, where the multiplication occurs the same number of times as the number of years that have passed. In each of the accounts, the value is growing, but in different ways. Fill in the blank lines in the following box. In account 1, the simple interest account, the values grow by adding the same constant number. This type of growth is called linear growth. In account 2, the compound interest account, the values grow by multiplying by the same constant number. This type of growth is called exponential growth. Now, if you have a choice between which of the two accounts that you would have, they're paying the same interest, exponential growth is always better. That's if you're the one getting the interest. Now, on page 129, we would start here, problem number 1. It says, here's a key observation about the repeated multiplication that occurs when finding the value of account 2 in the group activity. Repeated multiplication can be expressed more concisely using an exponent. Let's continue working with the two accounts from the group portion of this lesson. With an initial investment of $1,000 and 5% compound interest, the value of that account after 7 years will be given by 1,000 times 1.05 to the 7th power. Okay, so with that in mind, says number 2, without using a calculator, write that expression without any exponents. Don't perform the calculation, just write out what it would look like. So it'll be 1,000 multiplied by 1.05 7 times. Okay, now it says, what is the value of the account after 7 years? So what we could do, we could put this in our calculator. So we have 1,000 times 1.05, and then we would take that to the 7th power, which would give us, so 1,000 times 1.05 to the 7th power will give us $1,407.10. Now, on account 1, where the interest is simple, the account value goes up by 0.05 times 1,000, which is equal to $50 each year. Write a calculation that will find the value after 7 years. Then find the value. So you have $1,000, which is what you started with, and then you would add 7 times $50. So that would give us $1,350. Okay, now we're going to go to the top of the next page, and it says here, let's take a stab at summarizing what we've learned about linear and exponential growth. Use the calculations for simple and compound interest on the page as models. With linear growth, the value at a certain time is calculated using starting value plus a constant times a certain number of time periods. With exponential growth, the value after a certain time is calculated using starting value times a growth factor raised to a power. Number 7, without trying to give away the answer to question 6 too much, part of it involves a power. What is the significance of the exponent? It's the number of times that interest has been calculated, or the number of time periods. Okay, now look here, this tan box here. It says when a quantity increases based on linear growth, the value after a certain number of time periods can be calculated using the pattern. New value is equal to original value plus amount of growth per time period times number of time periods. When a quantity increases based on exponential growth, the value after a certain number of time periods can be calculated using this pattern. The new value is equal to original value times 1 plus the growth rate as a percentage to the power of the number of time periods. Okay, so number 8, it says use what you've learned about linear and exponential growth to calculate the value after 20 years in each of the accounts we've been studying. Make sure you write out the calculations you did. Okay, so we have account 1. We have $1,000 plus 20 times the $50, and that would give us $2,000. The account 2, we will have $1,000 times 1.05 to the 20th power, which is equal to $2,653.30. Now, we need to move on to the next page. Now, number 9, if you borrow $500 at 3% simple interest, the amount you owed after 4 years is given by, it'll be 500 plus 500 times 0.03 times 4. To correctly evaluate that expression, you'll need to remember the order of operation, which says that multiplication comes before addition. Now, number 11, it says evaluate the expression to find how much you'd owe. So if we take this expression, we take the 500 plus 500 times 0.03 times 4. We can put that in our Desmos calculator. We have 500 plus 500 parenthesis 0.03 close the parenthesis and another parenthesis here times 4. So that would give us $560. Now number 12, it says perform the following calculation, then compare your result to question 11. Describe what you did in terms of order of operations. So we have 500 times 1 plus 0.03 times 4. So if we show this would end up giving us 500 times 1.0, well, actually, no. With the order of operations that we just talked about, you will multiply these two values, which would be 0.12. So it would be 1 plus 0.12. So this will end up being 500 times 1.12, which is equal to 560. Now, if you notice here, the answer is the same for 11 and 12. So we could put the answer is the same. The multiplication inside the parentheses comes first. Then the addition. Finally, multiply by the result of the parentheses. It's a lot that went into that answer, but we actually did it. So now we go here to 13. It says the reason why you got the same answer for question 11 and 12 is the distributive property of multiplication over addition. You did get the same answer, right? Yes, we did. It says here, describe the property you referred to in question 13 in words, then make up an example of a calculation that uses that property. To multiply something by a sum or difference, you multiply that thing by each of the terms in the sum or difference separately. And then they want us to give an example. An example would be 5 times 3 plus 7. You can multiply 5 times 3 plus 5 times 7, which is equal to 15 plus 35, which is 50. Okay, now that concludes section 2.1. So if you have any questions, please email me and I will gladly answer your questions. Have a wonderful day.